In this final video of the Calculus 2 sequence, I would like to take a few moments to really reflect on one of the more beautiful mathematical results that I think you'll come across in your time studying calculus. And this one's called Euler's formula. This relates the functions e to the x, cosine of x, and sine of x. Okay, let's see how it works. So let's first remember what the Maclaurin series for e to the z is. I'm going to use a z here instead of an x, just because in other areas of math the z sometimes denotes a complex number. And what we're going to do with this Maclaurin series is actually plug in a very specific complex number for z and see what happens, basically. So just try to investigate. So remember though that the Maclaurin series for e to the z is 1 plus z plus 1/2 z squared plus 1 over 3 factorial, so 1/6 z cubed, etc. And we could write some more terms, maybe we will in a few minutes, but in sigma notation this can be written as the sum n from 0 to infinity 1 over n factorial z to the n. Okay, and like I just said a moment ago, what we want to do here is we want to plug in a very specific value for the z, and that value that we're going to plug in is just going to be the number I, the imaginary number I, times theta, so the variable theta here. The variable theta is actually a real number in this scenario, and so the number we're plugging in is what we call a pure imaginary number, because the imaginary unit here, I'm sure you remember, is defined to be the square root of -1. And what we end up with then is this relationship between I and 1 in terms of like a unit circle in the complex plane. So what we end up with is this relationship where the number 1 is of course over here. So 1 is equal I to the 0. Up here, here's our number I. I is equal to I to the power 1. As we move around, this number over here is -1 on the real axis, right? So this is our real axis, and this is our pure imaginary axis. -1 is equal to I squared, and we can see that just by looking at this equation. I equals the square root of -1, so I squared is equal to -1. And then finally, at the bottom of this circle, we have the number -I, and that's the same as I to the power 3. And as we work our way around this circle, these powers of I call this the circle of i's, but this is the powers of I, just rotate the plane by pi over 2, and eventually what we end up with is a lot of repeats, right? So we end up back over here. From I cubed, we multiply by another I, and I to the 0 is the same as I to the 4, right? And so there's a cyclical relationship here, and this is where the sines and cosines are going to come in, because sine and cosine have the same kind of for periodicity, right, cyclical relationship when you think about their derivatives and how the derivatives of those functions are related to one another. So without even working this out, hopefully we can see that there is at least a good possibility that this, at least the I number, right, we haven't done anything with the exponential yet, but there's a good possibility that multiplying repeatedly by powers of I should be related to sines and cosines somehow. All right, well, let's get into it then. Let's stop wasting time, right? What we want to do is plug in this value of z. So we're going to plug in for z. In our power series for e to the z, we're going to plug in I times theta. Okay? And so remember, the other thing that we should say before we get too far here is that the radius of convergence for the Maclaurin series for e to the z is plus infinity. And what that means is that we can plug in any real number, and we know that the power series representation, the Maclaurin series, is equal to the function e to the z for any real number z. What it also means, though, is that we can actually plug in any complex number. Okay? So this radius of convergence is not just the radius when thought of as like the x-axis itself. It's actually the radius that you would get by kind of rotating that around and filling out an entire disk in the complex plane. So there's a horrible rendition of a disk being filled out. So the idea, though, is that we can actually plug in any complex number and expect this to converge. It will converge. All right, so let's finally do it after all this buildup. The number e to the I theta is equal to the power series, n from 0 to infinity, 1 over n factorial, and then replace the z in the formula with I times theta quantity to the power n. And then let's write out at least the first 6, 7, 8 terms, 10, 12, whatever. Let's write out at least the first few terms, okay? So we start with 1 over 0 factorial plus the next term is I times theta over 1 factorial. The next term is I squared theta squared over 2 factorial, and this process continues. We get I cubed theta cubed over 3 factorial, I to the 4th theta to the 4th over 4 factorial, etc. And as we write this out, we start thinking about what's going to happen here. So we've gone 0, 1, 2, 3, 4, 5. Let's do at least 2 more here. So I to the 6th, theta to the 6th, 6 factorial, I to the 7th, theta to the 7th over 7 factorial, and then obviously this is going to continue. So I've written out here probably a lot more terms than you expected me to, but there's a lot of terms here because what we will do now, one of the reasons I drew this circle of i's here is because the powers of I can all be reduced to be represented by either a 1 or a minus 1 or an I or a minus I, right? As you go around the circle, you just keep going back and forth between 1, I, negative 1, negative I, 1, I, negative 1, negative I. And that pattern is going to go all the way through here, right? So when we look at the first couple terms, we have 1 over 0 factorial plus I, I'll write here, times theta over 1 factorial plus, and now we get to this negative, this I squared, right? I squared, if we go by our circle, is equal to negative 1. So this is actually a negative 1 theta squared over 2 factorial plus, same thing here with I cubed. I cubed is a negative I theta cubed over 3 factorial. And then this process of 1i, negative 1, negative I is going to repeat, right, as we go around this circle one more time. And we get to this point. So we now have 1 theta over 4 times 4, theta to the 4th power over 4 factorial plus I times theta to the 5th over 5 factorial plus negative 1 theta to the 6th over 6 factorial plus negative I theta to the 7th power over 7 factorial, etc. All right, and now you can probably guess what we're going to do. We're going to break this up. So by the way, again, we go back to this radius of convergence being infinity. Not only is this series convergent, but it is absolutely convergent. And I'm sure you remember that I harped on this in a video a few sections ago, but one of the consequences of absolute convergence, right, so we have absolute convergence for this power series, one of the reasons that we care about absolute convergence is that you can change the order of the sum of the terms in the sum, right, without changing the answer to the sum. So you can change the order of the series and not change the answer for an absolutely convergent series. And this series is absolutely convergent. So what we can do is pick out all the terms that have either a 1 or a minus 1. Okay, and we can write those first. So these first few terms, when we write these out, these are I'll put some big parentheses here, very big, because what's going to happen, we're going to have 1 over 0 factorial minus theta squared over 2 factorial plus theta to the 4th over 4 factorial minus theta to the 6th over 6 factorial, and then this plus minus pattern is going to keep repeating, right? So those are all the terms that we had that were either a 1 or a minus 1. We group them all together, including all the infinitely more that come with it, right? And we just group it like this. Then what we can do is we can look at the other terms that remain. The other remaining terms all have either an I, right, or a minus I or a minus I, right? And as we go through these terms, we can collect these, and not only can we collect them, but we can factor out the I from each one of them. Remember, I is a complex number, but it's just a number, right? It's a constant. So it can be factored out of this sum, and we can write this as I times, big parentheses again, times all the terms that are left over, and these are alternating, right? We have plus, minus, minus. It's the same situation, right? So this first one is going to be theta over 1 factorial minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial, and then again, plus minus, the pattern continues, right? At this point, we take a closer look at the two series that are inside the parentheses, right? And these can be written in sigma notation. And this first one is the sum of all the even terms. It's alternating, and it's just the even factorials on the bottom, right? And so this one can be written as the sum. And it goes from 0 to infinity. It's only the evens. It's alternating. So it's negative 1 to the n over 2n quantity factorial theta. I wrote an x, but theta to the power 2n. Okay? The next term, we have this I out front. And what's left with this series? Well, this is just the odd terms, but otherwise it's the same, right? So it's the sum of all the odd terms alternating, starting with a positive term. So negative 1 to the n over 2n plus 1 quantity factorial times theta to the power 2n plus 1. All right, and now you can probably understand why I chose to use theta as the variable, because these two power series are series that we know. These are Maclaurin series of very well-known functions. In particular, this first power series, the even terms, alternating even terms, this is the cosine of theta. That's the Maclaurin series for the cosine of theta. All right, we've still got the I there, and now we look over here at the odd terms. Well, you can probably guess what this is, but we've worked this out, right? So the series of just the odd terms alternating with the odd factorials, that's the sine of theta. All right, and remember where this all came from. This was e to the I theta, right? And so what we've just done is used power series to prove this formula, which is called Euler's formula. All right, this is called Euler's formula. This is a beautiful result. It relates e to the I theta, the exponential of a complex number, purely imaginary in this case, with sines and cosines, okay? Sines and cosines. All right, well, we're not done here, though. So there's another equation named after Euler, which is very, very similar to this, but it comes from just doing the following little trick here. We've got this formula. This is true for all theta, all real numbers theta. Remember, I is an imaginary constant, so we don't have to worry about that even, right? But look what happens if you plug in the number pi for theta. Well, on the left-hand side, we just have e to the power I pi. This is an irrational number raised to imaginary unit times another irrational number. Okay, so that's a weird combination of irrational raised to a power of imaginary irrational. All right. On the right-hand side, though, when we plug in, what happens? Well, we have cosine of pi plus I times sine of pi. Those are trig functions. We know how to work those out, right? So what we get is e to the I pi is equal to cosine of pi is negative 1. Sine of pi is 0, right? And 0 times I is just 0. And so we get this equation. And if we make one slight little change here, you might think, well, if there's a 0 there, Justin, just get rid of it, right? Drop it off. But if we make one little change here and we add the 1 to the other side, then we get this formula, which is known as Euler's identity, which is really just a special case of the formula, right? But this equation here, e to the I pi plus 1 equals 0. This is called Euler's identity, and in my opinion, this is one of the most beautiful equations that you will ever see in your life, all right, in this universe, because this is an equation that relates 5 of the most fundamental constants that we know of, right? 0 is the additive identity, 1 is the multiplicative identity, pi is the ratio of the circumference to diameter of a circle, any circle that you ever find. I is the imaginary unit, and e is the natural number. And this equation relates all 5 of those numbers in this beautiful, beautiful, simple equation.